So first of all, next Monday,
No class.
no class, and instead, you guys will be attending the deep learning class, which is 586 at 1:30.
Yes.
Okay, same room over here. Okay, and okay, so there's a few other fundamental techniques that we need to learn so that later on we can get a better understanding how deep networks work and what are they trying to accomplish. So for example, in the last lecture I gave you an idea how autoencoders are essentially doing the compression just like a PCA, then decompression so that we can reconstruct whatever data was compressed, right? So PCA has one fundamental flaw in it, okay? So as we discussed, the primary goal of the PCA is dimensionality reduction. So how does it accomplish it? As you saw internally, it's based on the concept of eigenvalues, eigenvectors, correct? And eigenvalues of what? Eigenvalues of the covariance matrix. Okay, so covariance matrix tells us what's the relationship between one data item and another data item. So it basically is a complete interrelationship of all the data items with respect to each other. Once we create the covariance matrix, then we compute the eigenvalues, then we sort them by magnitude, and then corresponding to the highest eigenvalues, we create the eigenvectors. So, because today's topic is a continuation of the PCA, there's another technique called LDA, linear discriminant analysis. And it's a very important technique to understand because later on, like I said, through deep learning, we'll try to accomplish some of the goals that LDA does. So anyway, so that we can understand it nicely, let's review fundamental concept of PCA, right? So once again, covariance matrix gives us the relationship between each and every data with respect to one data item to another data item. So if you recall, an easy way to understand this is through the example of face recognition. Even though PCA is not the best technique these days for face recognition, it's the deep learning technique, but if we have a practical example in front of us, then PCA is very easy to understand rather than just going through equations, or this is how it works, right? So very quickly to recap, if we were given, let's say, 200 images, okay, suppose they look like some faces over here. Oh, Sushant, last time it was a little bit smaller, so if you can see maybe a little bit more zoom. Once I go to that side.
That's fine.
Okay. Okay, so let's say each is 100 by 100, right? Okay, so first thing we do is we convert it to a vector. So once we convert the 100 by 100 by picking the pixels in each row to a vector, right? So 100 by 100 will translate to, as you can see, 10,000 by one vector, correct? Okay. So one way to think about this is, just like we discussed, if we have, let's say, a data point in 2 dimensions, right? And suppose the coordinates are x of 3, y of 2. So alternatively, we can represent it by a vector as 3, 2. Okay, same way if we have 3 dimensions, let's say x, y, and z. if I have some point over here with x of 2, let's say y of 5, z of, let's say, minus 3, right? Alternatively, I could represent this by a 3 by 1 vector, 3, 5, minus 3, right? Okay, so just like with our x-axis and y-axis, or in 3 dimensions x, y, z, okay, we have a unit vector in each direction which has a magnitude of 1. So for example, the unit vector in the x direction will be x of 1, y of 0. Okay, the unit vector which has a magnitude of 1 in the y direction will be 0 and 1, right? Okay, so any point can be created as a linear combination of these basis vectors. So these are the orthogonal vectors, right? So we could say, for example, 3, 2 is 3 times the x vector plus 2 times the y vector, which is basically 3, 0, 1 plus 2, 1, 0. And you can see this will come up to be 2, 3, right? So very similarly, if we take a look at the image, each image gets represented by 10,000 by 1 vector, right? So what does that mean? That means it's a single point. So each image is basically one point in 10,000 dimensional space. Okay. Now, some of these dimensions are like we discussed as the background, so they are not as important, right? So that's where the PCA comes into play. It transforms this 10,000 dimensions into, let's say, 50 dimensions or 30 dimensions or 100 dimensions by giving us those dimensions where there's importance in the data, okay? So there's another very, very important concept that you should understand, and that's the concept of vector projections. So let's briefly cover that, because we'll be using projections in the LDA technique. Okay. So again, easy way to understand this is, let's say we have a two-dimensional data, x, y, right? And some point over here, x of 4, let's say y of 3. If I project this on the x-axis, what will I get?
The x component.
The x component, which is?
4.
Which is 4,
yeah.
right? Okay, so how do we get that? Think of it this way. In the matrix form or the vector form, this is 4, 3, right?
Mm-hmm.
Okay, which is basically a 2 by 1, right? Okay, what is the projection? What is the unit vector in the x direction? In the x direction, isn't it 1, 0?
Yes.
Which is also 2 by 1. So if I wanted to project this vector onto this vector, what we do is we do the inner product. Okay? So for example, if I did, let's say, 1, 0, so I did that transpose of this. So this will make it 1 by 2 times 4 by 3. So wouldn't I get the answer 4?
Yes.
Which is the x component. Okay, so very similarly, we can project any vector onto another vector by simply taking the matrix or the inner product. Okay, so let me give you the example of PCA as an example, right? If you recall, after we go through all this eigenvalues, eigenvectors, and so on, right? We come up with some basis vectors. Okay, so suppose we came up with 30 basis vectors. Okay, so those basis vectors, each one of them, see, just like over here, in 2 dimensions, each data was had 2 components, right? and the vector in a particular basis, like the x, also was two components. Okay, so so my question is, if I have one of the basis vectors, forget the 30 right now, forget this. If I needed one basis vectors for my images over here, what will be the size of that vector?
30 by 1. Oh no.
No. 2.
10,000.
Okay, let me repeat the question. Okay. If I have a two-dimensional data, and I wanted you to tell me, to give me a basis vector, what will be the size of that basis vector?
2.
2 by 1, right? Now, if I gave you certain images, and I asked you, give me one of the basis vectors,
10,000.
what will be the size of it?
10,000 by 1.
10,000 by 1. Okay? Because remember I said each one of these is a point in 10,000 dimensional space. Okay? Now let's pretend somehow, we'll worry about the details later, we came up with 30 basis vectors. Okay? So each one of them will be what? 10,000 by 1. Okay, pretend this is one basis vector. And here's another one. And suppose somehow, like I said, we came up with 30 basis vectors. Okay. So now if we have, so what would be the size of this matrix? Suppose I call this matrix BB.
10,000 by 30.
10,000 by 30. Okay, so now suppose what I wanted to do is, just like when I projected it onto this basis, single basis vector, right? I got some number, correct? Same way if I project it on this basis vector, I'll get a number. You guys agree? Okay, so what if I picked one of these images, which will be basically 10,000 by 1? So some 10,000 by 1. And now what I wanted to do is, see if I projected it on one of these vectors, what will be my answer?
A number.
Just one number. Because then I'll do a transpose of this, multiply by this, and I'll get that number, which will tell me the component of this in this particular direction. You guys agree? What if I wanted to know the component of this on these 30 dimensions? Like if I project this onto these 30 dimensions, then how many numbers should there be? 30, because there are 30 basis vectors. So how will I project this onto these 30?
10,000 by 1 transpose of 30 by 10,000 maybe.
Okay, if I did transpose of this, right?
Maybe 1 into 2.
Then multiplied by VV, what will I get?
30 by 1.
1 by 30.
1 by 30.
Yeah.
So that is the projection of this onto this basis space. Now, so in other words, now I have reduced the 10,000 dimensionality to what dimensionality?
1 by 30.
Only 30 dimensions. Okay, so that's what the PCA does, right? Okay, now next question. Okay, if we have the basis vectors, if I did the inner product of one with another, what will I get?
0.
10,000 by 1.
They are.
What's the question? Sorry?
1 number.
Okay, if I multiplied this vector with any of these columns, with another basis vector, what will be my answer?
0.
0. Because by definition, basis vectors are orthogonal to each other. See, take a look in 2 dimensions. 0, 1 times 1, 0. So x and y. If I did 0 times 1 plus 1 times 0, I'll always get 0. Right? Okay. So the answer will be 0. Basis vectors are orthogonal to each other. So now the next related question, how do we get these basis vectors? Because if we get up to this point, it's easy. Okay, any data that we have, so all we have to do is transpose that data, multiply by the basis vectors, and we get the reduced dimensionality, right? Okay, but how do we get these such that they are orthogonal? So this is where one of the algorithms is PCA. Another algorithm that I'll describe today is LDA. Okay, so let's now go into PCA, which you already know, but hopefully now it will start to sink in a little bit more. Okay, so first thing we do is we convert each to a vector, correct? So this is a point in a 10,000 dimensional space, correct? Each one of these is a point. Okay, I can draw 10,000 dimensions, but pretend here are the, if I have 200 images, this is where they are appearing. Okay, so as some of you who are in the deep learning, you guys saw, whenever we have a data which is far away somewhere else, what we try to do is we try to bring it with the mean of 0, so that around the origin our data is spread out. Okay, so how can we move this data around the origin? So we take the average of all of this. So if I have like 10,000 by 1, 200 of these, pretend there are 200 of these. So if I take the average of the top row of 200, then second, and if I compose that, right? And then subtracted each data item minus the average, then what will be the effect? It will get shifted over here. Okay, so that's the first step that the PCA does, right? So basically we do I minus I average. Okay, then we assemble this into a matrix. So all 200 will, see it will still be a 200 by, 10,000 by 1, right? So now we assemble it into a matrix. So this matrix over here, as you can see, what will be the dimension of this?
10,000 by 200.
10,000 by 200, perfect. Okay, so now we go to the next part. We do the covariance of it so that we can see how each one of these relates with another in our data set. So covariance, as you guys saw, could be, suppose this as, I make it a tilde sign over here. So this could be I transpose, or could be I transpose I. Okay, both over here, right? So if I did, for example, I times I transpose, then what will be the size of this matrix? So this is basically our covariance matrix.
10,000 by 10,000.
10,000 by 10,000. Okay, so that's one possibility. And then we will compute the eigenvalues. We will sort these by magnitude. Okay, so if I did eigenvalues of a 10,000 by 10,000 matrix, how many eigenvalues will we get? You guys agree? 10,000 eigenvalues?
Yeah.
Now if we sort by, sort these, let's say keep top 30. Okay, then corresponding to these top 30, compute eigenvectors. So what will be the size of each one of those eigenvectors? See, if it is a 10,000 by 10,000 matrix, right? 10,000 eigenvalues if I compute an eigenvector, each eigenvector will be same as the original matrix. It will be 10,000 by 1, right? So essentially, if I assemble those eigenvectors, okay, into, that's my basis space. Eigenvectors are orthogonal to each other. Okay, so that would be one way of doing it. What would be the other way of doing it? Instead of doing I times I transpose, we go to I transpose times I. Then what will we get? 200 by 200. If I computed the eigenvalues, how many eigenvalues will we have? 200. If I again sorted it, kept top 30, corresponding to those top 30, I created an eigenvector matrix. What would be the size of that?
10,000 by 3.
No, I'm going from here to here.
Okay,
200 by
30.
200 by 30. Okay, but like we discussed, that cannot be our basis vectors. Our basis vectors have to be the same dimension as our original data. So now we need to do one extra step to come to 10,000 by 30. So if this was 10,000 by 200, and if this is 200 by 30, what will I do to these matrices so that I get 10,000 by 30? No, no transpose.
Just straight up multiplication.
Straight multiplication.
Yeah.
I'll get 10,000 by 30, and that will be my basis. Okay, so is everybody feel comfortable with PCA? How simple the technique is? And what's the purpose? The purpose is to give us those basis vectors which are orthogonal to each other so that we can do a projection of our original data onto these basis vectors so that it can tell us the reduced 30 dimensions for our original data. Okay. Now, next question. Suppose we got, just double check I was running some program. Okay, it's still running. Okay. So now what we'll do is, as part of the recognition process, okay, so now let's go to the recognition process. After the basis vectors have been created, 10,000 by 30, what will we do now? Project every known data onto basis vectors. So I0 will be projected to, as we discussed, by going I0 minus I average, then transpose times the basis vector. So this will be 1 by 10,000, right? This will be 10,000 by 30. So what will be our answer then? Basically 1 by 30. Correct? So 10,000 by 1 dimension has been reduced to a 30-dimensional space, 1 point in 30-dimensional space. So same way we'll go to I1. It will get represented by 130. Same way we'll go to I199. It will get represented by 1 by 30. Okay, so now the next question. How do we do recognition? Suppose somebody gives us an unknown image of some person, right? Also 100 by 100. How will we know which one is these?
By computing the distance between, like,
Do projection.
Projection first, exactly. So first project it onto the basis. Okay, what will then this give us?
150.
1 by 30. And now we can compare those 1 by 30 over here with the second one, with the 201, see which one is it closer to.
Closer.
Okay, how do we compare a set of 30 numbers with another set of 30 numbers?
Calculating the error maybe.
Okay, one is Euclidean distance, meaning this value minus this value square plus the second value minus the second value square, right? There's also another formula, so one comparing to, let's say, 1 by 30, or whatever that size is, vectors. Okay, so there are different techniques over here. Okay, I'll just list 3 popular techniques. One of them is basically Euclidean distance. Okay, like first value minus the first value square plus second value, and then take the square root, right? Another one is called correlation. If you Google the correlation formula between 2 vectors, there's some mean, some variance involved. Okay, it's a standard formula. So we can see which one the incoming IX correlates to with our stored data. Whichever produces the highest correlation, that will be the data. Okay? So now let me introduce one more technique here, which is called K nearest neighbor. So this is a popular machine learning technique, extremely easy. So let me show you what the concept is. Okay, KNN, the fundamental idea is like this. Okay, if we take a look at our 200 data points, right? Pretends they are basically, so these are the 200 images. Okay, pretend this is person X. Pretend this is also, so let's pretend we have 2 images. Let's make it easier, 5 images per person. Okay, so let's say this person X, these are the 5, so in the 10,000 dimensional space, those are the 5 numbers corresponding to, or 5 points corresponding to person X, right? So same way, next 5 may be, let's say these are person Y, meaning a different person. Okay, so now suppose we get person X. Okay, one option is don't worry even about the PCA. Simply convert it to a 10,000 by 1 vector. Okay, as we discussed, this will, let me see if I have a different color. So this will end up showing, let's say, a point over here. Oops, this doesn't work. Okay, so suppose this is the point, right? So then what we try to do is, we try to see in K and N, K basically means, K is a number, so this is just a number. And N basically means nearest neighbor. Okay, so that's the NN, nearest neighbor. So we'll do a Euclidean distance to the neighbors and we'll sort them by whoever is closer. So if we take a look over here, you'll see this point is closer, right? This point is closer. And let's pretend this one is, person Z. So if we were doing a K and N with K equal to 3, okay, we try to pick K to 3 or K 5, usually an odd number, so that we can do a majority voting and see. Two of these neighbors are which one? Person X. One of them is person Z. So what are the majority of the neighbors? X. So this will be recognized as person X. Okay. So that's the third technique. So we can do it in the original 10,000 dimensional space. Or now let's take a look at the reduced dimensional space. We reduced it to 30 dimensions, right? So if we already have applied a PCA to all the stored data, so now let's take a look at, so KNN after PCA. Okay, so every data point was reduced to 30 dimensions. So again, let's pretend these are some, right? So the 200 points appear somewhere there. So now each point is in 30 dimensional space. You guys agree? If we did a PCA and reduced it to 30 dimensions. Same way we'll take a look at IX. Now we'll project it by multiplying it with our basis vectors to 30 dimensions. And again, we'll see if this is some point X, what are the three neighbors? If this is one neighbor, this is one neighbor, and let's pretend this says person Z. This one says person Y. And this one says person Z. So what will we conclude? Z. Okay. What if they were all different?
Tries again.
Then it's not one of our data points for it. Meaning it's not one of the 200 people. Maybe it's some unknown, right? Okay, that might be one possibility. So now my question to you guys is, which one will work better and why? Which one will give us more accuracy? Directly applying KNN on the 10,000 dimensional space, or applying KNN on the 30-dimensional space.
The 30 dimension.
Why?
Because in the 10,000 we have a lot of information, maybe doesn't really.
Yeah, some of them is background, some of them might be, somebody's long hair, short hair, whatever, which really for face recognition doesn't matter, right? So PCA already gives us 30 of those dimensions which are distinguishing the data most from each other. So obviously this will work better, right? So in your next assignment, okay, because I wanted to show you the actual KNN. Okay, so I'll give you the code for KNN, but you have to write the code for the PCA. I forgot to give you the library code so that you can easily see how to compute the eigenvalues, eigenvectors. I'll try to remember to do it, if not today, definitely tomorrow, so that you can start on it. But as you can see, now you can see there's really, once you write the code, it's not more than 20 lines of code, hardly, right? Provided you have the library which will do the eigenvalue, eigenvector calculations, okay? So anyway, so this one will work better, right? Okay, so the other thing that you should really understand is, so one was the concept of the projection, as we discussed, how we project the high dimensional data to a lower dimensional space. Second concept was